In this session, we will introduce the challenges in speech recognition and some suggestions to solve the problems. In speech recognition, there are some conditions that will affect the recognizer performance, such as far-field theme, background noise, channel distortions, accents and dialects, emotional speech, disfluent speech, topic change, and so on. Factors such as environment and channel cause speech signal distortion. Voice signals will be affected by context and change. Differences in the speaker and accent will lead to differences in the distribution of voice features in the parameter space. Psychological and physiological changes in the same speaker bring about the phonetic changes. Different pronunciation methods and habits cause changeable phonetic phenomena such as omission and continuous reading. Such kinds of situations make the recognition task difficult and need new techniques to improve the recognition system. Compared with a near-field speech recognition, the challenges faced by far-field recognition are mainly caused by the complex signal propagation environment. The long distance makes the signal-to-noise ratio of the received signal low. In a closed or indoor environment, there are various diffuse noises, such as and background noises in the environment and the amount of reverberations. In the far-field recognition scenario, there may be many people talking at the same time, causing the cocktail party problem, which is often referred to as the multi-source signal interference detection problem. In addition, there are echo interference caused by the returning sound from the far-field playback device. Far-field speech recognition needs to solve this problem by means of the techniques of speech enhancement and speech separation to extract or separate the targeted speech efficiently. Speech front-end processing refers to process the original speech before feature extraction, partially eliminating the influence of noise, reverberation, and different speakers so that the perceived signal can better reflect the essential characteristics of the speech. Front-end processing is necessary in many speech processing systems, like speech communication, recognition, and synthesis. The front-end processing model mainly solves the problems of far-field recognition by introducing traditional microphone array technology or deep learning speech enhancement methods. The very basic and important work is to accurately model the sound propagation environment, thereby designing optimal speech signal enhancement algorithms and helping to quickly generate a large amount of far-field speech data for acoustic model training in the recognizer. The speech recognition engine is very sensitive to the nonlinear processing of the speech signal. So, the front-end processing and speech recognition process should be jointly optimized. There are mainly three approaches coping with background noise. The first one, try to remove the noise without distorting the speech through speech enhancement. The second one, choose a set of features that are inherently noise resistant. For example, positions of peaks in the spectrum. The third one, extend the statistical model of speech to model the noise as well. If we have 1,000 states in our speech models and 4 states in our noise model, we can think of this as a single 4,000 states model of both speech and noise. The average power spectrum of one of these combined speech and noise states is just the sum of the average speech power spectrum and the average noise power spectrum. The recognizer uses the 4,000 state model and simultaneously recognizes both speech and noise. Number of states in the combined model is the product of the number of states in each model separately. The task cannot afford to have many states in the noise model. Telephone-based systems must cope with a wide range of microphones. Microphones vary greatly in their frequency response. The speech spectrum is multiplied by the channel frequency response. That's to say, the speech spectrum has the channel spectral response added to it. The system can correct for this by subtracting the long-term average of the spectrum from the spectrum calculated for each frame, which is called spectral mean subtraction, and makes the recognizer immune to variance in channel frequency response. Under matched training and recognition conditions, the use of spectral mean subtraction increases the error rate slightly. Speaker adaptation can adjust the recognizer to suit a particular speaker. For the supervised adaptation, computer must be told each time it makes an error. For the unsupervised adaptation, computer assumes that most decisions are correct. For the incremental adaptation, the adaptation goes on continuously. We need to adapt the entire recognizer based on a small amount of speech by use of a form of general transformation, such as linear or nonlinear mapping of the frequency axis. Linear transformation of the feature vector, that's to say multiplying by a matrix. There are different linear transformations of the feature vector for different states, using the same transformation for similar sounding states. Error rate can be reduced from 7.9% to 7.2% when the recognizer is told when a new speaker has started talking. Most recognizer evaluation uses a people rating from a prepared text. Performance is much worse with carol speech. Unscripted speech contains mumbling with less clear articulation, large speech variations, false starts, repetitions, and corrections. Language models are specific to one application. For example, language model for Wall Street Journal will not work well for engineering literature. N-gram language models are crude and brute force that cannot generalize to new words. Under such conditions, the recognition is a task independence. Language models based on classes of related words would generalize them more easily. However, it is difficult to choose the classes, which could be names of colors, makes of cars, and so on. The classes could also be nouns, adjectives, verbs. Many words need to be in more than one class. Small vocabulary recognizer uses one mode for each word, plus silence, noise, cough, and so on. Typically, the recognizer has 10 to 15 states per word, totally smaller than 2,000 states. It needs training examples of each word. Speaker-dependent task means single user has more than 10 examples of each word. Speaker-independent task means many different users and has more than 100 examples of each word. The performance with no grammatical constraints on word sequence for recognizing digits 0 to 9 is smaller than 1% speaker-independent error rate, and for recognizing alphabet A to Z is smaller than 10% speaker-independent error rate. This is a hard test because many letters sound similar. For example, B, C, D, E, G, P, T, and V. Large vocabulary recognition task has problems with recognizing large vocabularies, more than 1,000 words. The searching task is now enormous with array alignment plus word sequence, and is essential to have a good language model to limit the number of possible word sequence. The task needs very large memory requirements to store all the models. More of the words are highly confusable. The recognizer needs to improve the acoustic modeling. Simple Gaussian assumption is no longer good enough. The GMM-based feature space expression may need 20 Gaussian functions parameters to describe distribution instead of only 2 functions. Huge amount of training data required hundreds of hours of speech. The recognition system must usually be able to recognize words that are not in the training data. The research of large vocabulary continuous speech recognition LVCSR with natural dialogue style is a hot and difficult point of current research. That's all for this chapter. See you next chapter.